So let's welcome Amat Cama, also known as Aces, from Shellfish. He will talk about video game exploitation and more specifically Source Engine.
All right. Hi, everybody. As he just introduced me, my name is Amat, and I'm pleased to share this topic with you guys today. So today I'll just go first with a brief introduction, and then basically you can just look at this agenda and you know what we're going to do. I'm not going to go through all of these. All right, so as he said, I play CTF with Team Shellfish quite a lot. I'm a senior security researcher at Chaitin Tech, and this is a startup based in Beijing, and mostly it was started by some CTF players, and they provide pen testing services, but recently they just started a security research lab, and I guess last week we were at Pwn to Own, and we've taken part in other contests such as Geek Pwn, and actually this project was a Geek Pwn awardee, so in 2016. All right. Actually, also a lot of people on that team are from Team Bloop. I don't know if you know, it's just a merger between Blue Lotus and Oops. Okay. So first, I'll just talk about the prior work that has been done in this area, because I think it's worth mentioning. Basically, these two guys, Luigi and Donato, are the guys that have looked at game engines in the past. They did quite a lot of work, looked at a number of different game engines and actually found a lot of bugs. So if you guys are really interested, you can read all their different papers. They talk about ideas, the bugs they found and everything. Yeah. It's a bit old though. So why did I want to look at this? To be honest, just because it's fun. So I can give you a bunch of other random reasons, but I really just wanted to do because, you know, it's just fun, and not a lot of people have looked at this, so I was hoping it would be easier to find bugs in here. And people play these games every day, millions of people, so it should have a big impact to find bugs in these things. All right, so what is a game engine? So basically, it's just the kernel of the game, right? So, you know, basically you can have a game and just have to rewrite everything from scratch every time would be quite painful. So game developers tend to just keep one component so that they can reuse it in their different games. So they just provide different things like AI, networking. Networking is really important if you want to play multiplayer games. You don't want to write that every time, right? So graphics and memory management. Scripting is interesting because some game engines provide scripting engines and they just make things go faster. So basically all the functionality is exposed through APIs. And then you end up with like a SDK that you can use to write all your games. So they're customizable, and for example, you can have one game engine and actually end up with really different games. Counter-Strike and Dota use the same game engine, but when you look at those games, they look really, really different. And yet the game engine is versatile enough to be shared between two different games. So here are some popular ones. I like Frostbite because basically I play Battlefield and FIFA. So Unreal Engine, I don't know much about Unreal Engine, but it seems to be very popular. And today we're going to be talking about Source, which is the engine for Team Fortress, Counter-Strike, and Dota. And this is actually the old version of Dota because there was a Dota rewrite in the end of 2015, and it uses Source Engine 2, which is a bit different. So Unity, I guess some CTF players might know about Unity from like Ghost in the Shell Code, Pwn Adventure. And apparently during this CTF, there's going to be a Unity challenge too. So, and CryEngine, I don't know anything about CryEngine. So, all right, let's talk about bugs. So, just a bit of bug theory related to game engines. So, like I said before, they're very customizable. If you can find bugs in the custom code, it's pretty interesting if, I guess, you're just targeting one game. I mean, some games are popular. It's fine to find bugs in just a game, but if you find bugs in the engine's core, that's much more interesting because just that bug can affect many, many more games. All right, so now let's talk about source. So it's pretty old. Apparently, it's actually has its roots from like 1998. The original Half-Life, they were using a engine called Gold SRC or something like that, and the developers, I mean, this is what I read online. The developers said they already, before the game was released, they were already working. They already had to start working on newer projects, so they decided to turn like the core of Half-Life into a game engine. So the architecture and features of Valve, of Source, it has basically everything a game engine is supposed to have, and just like we discussed in the previous slide. And additionally, it has Steam integration. For those of you that know Steam, it's just this platform where basically you can just play games and keep scores. Everything is centralized. And it makes sense since Steam is also owned by Valve, so it would be weird if it didn't have the integration. So an interesting thing is networking. So multiplayer networking in Source is client server. You get a central server just taking care of everything as opposed to a peer-to-peer network. So the server is in charge of simulating the world, game rules, and actually even player input processing. So basically, you will press a key or like a mouse click, and the information will go to the server, and the server will kind of tell your game client how to move or whatever to do. And yeah, the client will just connect and obey orders. Most of the communication is done through UDP, and UDP is preferred because TCP has so much overhead, and they just end up re-implementing some kind of TCP over UDP. So they have to take care of packet splitting, fragmentation, reassembly, compression, decompression, encryption, anything they just want to add in there. Some parts are kind of are optional. So different games will do different things at this lower level. Some have encryption, some compress using different algorithms. So in this area, it's a bit complex parsing. So there's a chance to find some low-hanging fruit bugs here, but I didn't look much into this area. So if anybody's interested, this is a good place to look. So the game, so just like any game, there's this concept of a tick, basically, which is just a discrete time interval that says at every tick something will happen in the game. Just, at every tick, a player will move. At every tick, somebody will die, whatever. So the server will just take snapshots of whatever has changed in the world and send it to the different clients. And of course, it won't send everything to every client, but at least whatever is relevant to that client will be included in this snapshot. So snapshots is just like a chunk of information, like a delta of what has changed from the previous tick. And the client is the one responsible for sampling user input and sending it to the server. So the communication is done through some messages, I call them. There's just three kinds. Some are sent by both the client and the server, some from the client, some from the server, and that's what I mean by client messages are actually the ones that the client sent. So just not the ones sent to the client. And if you're looking for RCE type bugs, this is a great place to look in. You know, there's a number of different messages and a lot of code to look at. So if we look here, we can find some bugs in the client, right? And if we find bugs in the client, we can have a evil server and attack a client. But we can also find bugs in the server, and with an evil client, we can attack the server, or we can just find bugs that affect both, and pretty much we end up with, like, I don't know, we can make a worm or just this bad botnet of high performance gaming machines. So these are the bidirectional messages in source. They're all prefixed with net underscore, and there's not so many of them. And the ones that we are interested in are the tick and string command. With tick, we already talked about. We'll talk about string command in a bit. And as for the client messages, they are all prefixed with CLC underscore X, and we just care about the response CVAR value. We'll talk about CVARs. Maybe some of you already know what CVARs are. They're pretty common in games. And as for the server messages, they're all prefixed with SVC underscore, and we're just interested in these four here, and we'll describe what they are also. Actually, about these server messages, there's a number of them. And these are actually the ones that the client will receive and parse. So they're a good place to look since there's so many of them. So SVC user messages, we just saw them. These are also server messages. And basically, they're kind of game-specific messages. And they can differ from game to game, but some of them are actually shared, and they're a subtype. They're a subtype of the SVC user message, and you can see how they're sent. You send a SVC user message, and then user message is contained inside. And here are some examples of them. Just show menu, process, whatever. And vulnerabilities here have a high chance of being present in just that game. Network entities. So basically, everything in the game world is a entity, even the game rules, the players, objects, whatever. So basically, entities define the whole game, and these are what are being sent in the snapshots. And I guess they're just everything. Without entities, you don't really have a game. The networking system will make sure that they are synced between the client and the server. Some entities only live in the client, some only in the server, but most of them will be shared between all the clients and between the client and the server. So so instead of sending, like I said earlier, instead of sending everything to the client, only the entities that matter to that client will be sent. So basically, as this ugly diagram shows, only the things that the client can see, also the things that the client can hear will be sent. So no information about D will be sent to this guy here. So yeah, so like I said, exists both server and clients. When the server sends a SVC packet entity message, entities that, if they refer to an entity that doesn't exist in the client, they will be automatically created. And the maximum number of entities is this number here. So convars and concommands. Convars are basically just configuration parameters. So they can change like some aspects of the game. So Some interesting ones are like bot don't shoot, you know, the bots in the game won't shoot at you, or like host map is the name of the map. And console commands in source, they're actually convars and they just have a type that says command, but basically they're the same objects. And some interesting one would be retry. The client will just retry the connection to the server, and gods, all players are just invulnerable. So if you want to cheat, you can use these. This command here, this is a command that just lists all the commands and CVARs. All right, so if you want to get the value of if the server wants to request the value of a CVAR, they will use get CVAR value, and the client will just reply with this message here. And the next net string command is can be sent by both the client and the server, and it's just the cont commands that we saw. So message encoding, you know, transmission, reception, basically everything is encapsulated, is encoded in different ways. The default is bit streams. So for example, they won't send a full int, but they'll just encode it in a way that only the bits that matter are sent. This can be customized. For example, Counter-Strike uses Google protobuf instead of the default bitstream format. And compression and encryption are all optional. So now let's talk about hunting for bugs in source. So where to look? We saw in the previous slides, you know, there's many places we can look. The messages are very interesting if you're looking for remote attack vectors. So there's a number of DLLs and shared objects in the game. Engine.dll is the engine core, and client.dll is basically where most of the game-specific code lives, but there's also a lot of template code in there that's provided by the engine. Other areas that we can look at, game maps, you know, they have this custom format called BSP, and you can make custom maps, and whenever a client connects, they'll download this map and parse it. So you can also find some good bugs here. And message of the day, you know, just whatever. It could be a web page. So I think source is using Chrome. So if you want to find bugs in Chrome, you can do that. There's also audio stuff, you know, file formats or whatever. So now I'm going to talk about a bug in Team Fortress. So the create string table command. This is a server message and is used just to create string tables, which are just a way of avoiding sending the same strings or binary blobs over and over. So you just store them in a table, and when you want to reference them, you just use an index. So when a SVC create string table message is sent, eventually the message will get you know, just deserialized and everything, and then an object like this is created with all the contents inside, and basically this is the message that processes the command. This is the code that processes the command, and here data in is some data that we control. Read. So I simplified this code. It doesn't really look like this, but I just simplified it to make it easier to read. So all this stuff here, dest len, source len, we control, and as you can see, they're just ints, and there's 2 overflows here, and I guess well, we can just trash stuff. And the thing is, these aren't really this won't result in like a unbounded copy, because the read bits function will just read as much data as is available. So you can still specify values here that will cause the overflow, but if you don't send enough data, it'll just not read as much as what's specified here. And yeah, that's good enough. So can we exploit that bug? I guess we can corrupt adjacent objects on the heap, you know, C++ or whatever. but also we can attack the the heap allocator. Here is tcmalloc. Tcmalloc is kind of, I mean, I guess there's no security considerations. If you check out this article here, it just tells about how you can bring back the old write, what, where stuff, and unlink bugs or making the heap return arbitrary addresses. But sadly, this bug is not present in Counter-Strike. So instead of trying to exploit it, let's just keep looking. So now this is a user message. So if you guys remember user messages, so we don't really care what this thing does, but what we care about is looking at the function that processes this, right? So this is the function that processes that message. Again, it has been simplified a lot, but basically, ent IDX, we control it, and we're indexing into an object without any bounds checking. This is also like a out of bounds, right, of whatever we want, and this object lives on the heap. So again, can we exploit it? We can just do everything we did with. We can just try to do the same things as the previous bug, but sadly, this one is not present in Team Fortress 2. So we should just keep looking instead of trying to exploit it. And so now, maybe we got lucky and we found a bug in the core. And since I'm a lazy person, this is better because we don't have to exploit each game individually, and just we can use one bug to target everything. So the packet entities, if you were following earlier, remember entities are basically everything in the game. And this message here is what you use to send information about them. So, I mean, there's a lot of code that before reaching this function, but I'll just spare you that. This is where you end up if you send the correct stuff. And basically, this object here, we control a lot of fields in there. We control this and we control this. So as you can see here, we have a signedness issue, right? New entity is an integer, and they're just checking if it's greater than 2048. So it can be negative or whatever. And what happens here? So we use that new entity value to call this get client networkable function. And what that function does is just basically this, it just index into some stuff. And so whatever it returns will be interpreted as, if it's not null, will be interpreted as a C++ object, and it'll just be, a method will be called from it. We don't care what that method is. So can we exploit this? The entity list is a global object in the client.dll, and its field, this field, is a static buffer of size 2048, right? That's total number of supported entities. So if we can retrieve a C++ object by triggering that bug and accessing data out of bounds, we can just we can actually control the program count. So this bug is present in the engine core, so I think we should try to exploit this one. So about exploiting this bug, so we want the index, we want to index something that we control, right? So basically the arithmetic ends up being, this base plus the offset to that array plus our index equals fake object. But IDX is an integer, and we need to have it negative if we wanna pass that greater than check. So luckily it's multiplied by 8, so we can just make it wrap around and be a positive value. So now we need to find a way to store control data in the global data section of client.dll. So how are we going to store data? We can look at the user messages. Remember those if you were following. So the show menu message is used to display like HUD menu on the game. I don't really play these games, so I don't really even know. But it's just gonna display something on the client screen. I don't know. This function will buffer some string data, so you can send the message in multiple parts, and the buffer is a global buffer in client.dll, so we can store data we control in client.dll. So what we're gonna do is just send this show message to store a fake C++ object, and then we can trigger the SVC packet entities bug, right? So we end up with something like this, right? The array is here, our object is here, we index, and we just got our stuff here. But I guess some CTF players or whatever will soon figure out that, oh, damn, we got a leak, right? If we don't leak anything, we just can't exploit this bug. So let's have a look at the rest of that vulnerable function. So we see that if so in the case where indexing that array returns null, we will call this create DLL entity. So remember, when the entity doesn't exist on the client, we'll just automatically create it. So in that case, we'll just call this function to create a new one. So that function will create the entity if it doesn't exist. And eventually, we end up in this add entity at slot function. And in the listing here, we see entity array. This is different from the other array. So apparently, there's like a caching array and a real array, I guess. And basically, this one is also indexed, and we just update the information and create a new object there. So now we have two arrays, this one and the other one, and we have one index used to index in both of them. So we can basically we can simplify how these arrays are accessed by just saying they share a base, and the index is used in different ways to reference each of them. If the value fetched from the first one is null, we will write the pointer to a C++ object in the second one. So we have something like this, the index here is null, so okay, let's create a new object in here. So now we have an index, right, of a C++ object, right, using the same bug. And if we can read it back as a string, then we can leak its vtable, which is its vtable pointer, which is which actually will help us get the base of the client.dll module, and then we can use Rob gadgets in there or whatever. But how are we gonna do that, right? Remember those CVARs, for those of you that were following? So some CVARs are stored in the global data section of client.dll, and so we can target those ones. So each CVAR has like a char star field. So if we replace this char star field with a C++ object pointer and query that CVAR back, we can actually leak this way. So basically, we just need some kind of algorithm. I don't know what language I wrote this in. This is just random stuff, but just so you just need to do this if you want to find some good CVAR targets to override. So the attack plan looks like this, right? The server sends this SVC packet stuff to corrupt the CVAR. Then you request that CVAR. The client responds. You send the user message to store your data in a global buffer. And then you trigger the bug again to, divert code execution. But we have a problem. Due to the integer overflow and the one index being used in two arrays, we end up failing a check in that same vulnerable function. So after the new entity is created, it will check to see if it's actually where it's supposed to be. And if it's not, we get this host error thing. And actually, host error means the client will disconnect. And if the client disconnects, the only way we can make them reconnect is by them connecting again, right? And this is kind of lame. We don't want to have to, call the guy and say, hey, connect again to my server. So we need to find a way to make it happen automatically. So you remember those con commands for the people that were following? So one particular command of interest is retry. So retry just means retry the connection to the last server. And of course, we can't send this after the client disconnects, right? But it turns out that there's a delay in command processing. So if we send a packet and then a command at the end of that packet, the packet will be parsed and processed, whatever, and then the command will still be processed, even if host error or whatever happens. So this way we can make the client reconnect even if it disconnects. So let's see. So the updated attack plan is gonna be so send this SVT, send this SVC packet entities to corrupt, and then you also send the retry command. The client does the host error, whatever. You wait for it to reconnect, then you. Actually, this shouldn't be. Oh, actually, yeah. Then you request the corrupted CVAR value to leak the, defeat ASLR, and then you send that show menu message to store data in a global buffer, and then you actually get code execution, and you can do whatever you want. So now I'll just show you a video demoing the attack. So actually, I guess I can explain a bit, but basically, I just started a server, and you can use Windows or Linux to host your server, but if you want to change the data being sent back and forth, you can, on Windows, you can use something like minhook to hook like receive to or send to, and on Linux, you can just use LD preload. So after the server boots up, I'll go to the client and search for the evil server. Oh, the client hangs. And then we get this stupid calculator. So basically, now let's talk about some conclusions, and you don't game engines aren't safe, and you shouldn't connect to servers that you don't know. So if unless you want something to happen to your computer, and things to try are fuzzing. I didn't get a chance to fuzz. I just couldn't think of any practical way to do it. So if anybody has some fuzzing ideas, I'm pretty sure you'll find many bugs. So how about attacking the servers instead of the clients, right? We can do that botnet scenario we talked about earlier. So you just hack a server and then you hack the clients, and then using those hacked clients, you hack some other servers, and then you can mine bitcoins or something. And also, how about jailbreaking game consoles through the engines? A lot of things like Xbox 360 or PlayStation 4, they have games using these engines. If you can find the bugs and then exploit them, you can do jailbreaking. I guess nobody has really done this before on these devices. So, and I think that's it. So, questions? All right. Oh.
Did you release your finding to Valve?
Yeah, of course, yeah. But I have not confirmed that they fixed the bugs or not. So, I mean, they did say they did fix them, but maybe you can double check and see if they're still there.
And why the Source Engine and not the Frostbite? Because you said you're playing FIFA and Battlefield.
Yeah, I guess. Yeah, that's a good question. Maybe that's the next one. Also, I guess another reason is maybe, just maybe, the Source Engine has like leaked source code somewhere, but I'm not sure.
When exploiting with the source engine, did Valve anti-cheat or any other mechanisms give you a hard time, or was that not even?
Yeah, so at first I thought you're talking about VAC, right? Yeah, at first I thought that would be a problem, so I had it disabled, but then when I enabled it, it didn't change anything. So, yeah. All right, so no more questions. Thank you.
Thank you, Amat.